It's my absolute great pleasure to be introducing Gilberto tonight. I had the great fortune of speaking with him on Zoom that we published onto LinkedIn a little while ago. And fact is, I definitely wanted to hear more. So he's Professor Dr. Gilberto Camara. He joined the Group for Earth Observations, or GEO, as Secretariat Director in July 2018. So he's known all across the community for his research in geoinformatics, geographical information science, land use change. Has been recognized internationally for promoting free access and open source software for EO, Earth observation data. Let me give you a couple of things that just amazing from his career. So under his guidance as Director for Earth Observation, this is back in 2001, and Director General at 2006 for Brazil's National Institute for Space Research. He made significant advances in land change monitoring using remote sensing. So this contributed to Brazil achieving an 80% decrease in deforestation in the Amazon rainforest. I'll read that again, an 80% decrease in deforestation, supporting Brazil's commitments. It was hailed as the biggest environmental success story in the decade. Now, I know that things have taken a downturn at the moment, which is very sad and difficult to come to terms with, but I absolutely applaud the work that Gilberto did. And one thing I've never asked Gilberto is that, according to my sources, he appears to be a knight. Is this true?
Well, Chevalier, a knight of the Ordre National de Mérite de France, yes.
It's rather cool, isn't it? That must come with some special privileges, I imagine.
Not so much, with special obligations, I would argue.
Super cool indeed. Thanks, Lavina. So, but I've probably done enough talking, at least for the time being. Do you need to share your screen?
Yes, please. So let me share my screen.
Pop that on now.
And please give me my. Okay, you probably need. Yes, and therefore I'm going to put this into presentation mode. Can you all see it?
Looks good, yeah. So
okay.
Over to you.
Thank you so much. I mean, it's an honor to be talking to you today. A fantastic invitation by Richard. Of course, the other speakers to which I'm honored to share the screen, the floor with Katerina Kalembi, which is a fantastic star, and Grega, which is a great innovator in Earth observations. So my talk is directed to more interesting, just to provocating bits, and it's called Ontology Meets Machine Learning. And I think for those of you who are not, let's say, in the game of Earth observations, some basics here. Why Earth observations are valid? Why are they so important? First of all, they are objective. We measure, so it's a measure of the Earth, and continuous measuring of the Earth of different resolutions, different bands with different satellites, and of course covers inaccessible areas: the oceans, the Amazon forest, Siberia, the Arctic, the Antarctic, and so on. You have so much information, and a lot of it is real time or near real time. But you also have the historical record going back to the first satellites, which were in the 70s. So this is, you cannot imagine a world where you think about the Earth without having the power of satellite data. The other bit which is relevant is the fact that many agencies have adopted open policies. This was not the case a decade ago, but this has changed significantly. And now Brazil, China, Japan, Europe, US have now said, oh, our satellites, the satellites which are financed by the public purse, they are open, which means you have more data than ever before, and more data than you would ever be able to process. This creates a very interesting challenge for those who want to do it. And obviously, you guessed it, this is, of course, tailor-made for this new generation of technologies, which combine, of course, cloud services with, I'm going to use the term machine learning in the whole, but in a very general sense of computational techniques of data processing. And therefore, in the area, and since I think this is more the Milton Keynes AI groups, there has been a search and a very welcome effort of, let's say, organizing. The first thing you have to do, you have to organize that data. It's data does not self-organize. You have to come up with, well, you have to organize things, consistent observations, which we call in the jargon data cubes. And then one wants to apply machine learning techniques or other similar, but I'll focus today on machine learning because, of course, a lot of you are interested on it, and of course, there's a lot of interest globally on this matter. Now, question obviously that comes about is, in what way is the big spatial data special? Just a moment. So, I mean, this is the view. This is not my slide. This is from Cassie Korzikov from Google. And I mean, this is the standard way of talking about machine learning. You have your data as ingredients, your algorithms as appliances, your models as recipes, and your prediction as dishes. So, I mean, this is what puts into people's minds. And the point here is that there are a lot of unstated, as anyone who actually has tried to do cooking at home during the pandemic has found out. There is a lot that's unstated in the recipes. You know, when I cook here, I look at the recipe and my wife just say, ha, ha. And I say, how much do you judge? How much curry do you put? And she says, no, I just know how much is right. And this is the kind of things that anyone who has tried to learn cooking has found out. It's just not a question of pushing the recipes down the predictions, but more of that later. The success of machine learning, in fact, has come about on a fairly, we'll say, I'm going to argue here that's it's a very specific kinds of data sets. Of course, things like face recognition, automatic translations, chess, Go games, a number of interesting, I'm a chess player and I'm absolutely flabbergasted by the AlphaZero product. But is this the case for big spatial data? And is there something that, you know, you would apply to Earth observation data that breaks your hypothesis that you have for machine learning? And I'm sorry to report, there is an elephant in the room. And of course, elephants, real elephants in this case. So this is a real picture of an elephant in the African savannas. And there are savannas in places of the world. There are savannas, for example, in Brazil, but there are no elephants in the savannas in Brazil. Simply because they were exterminated, well, not the elephants, but the megafauna that existed here at 20,000 years, was exterminated when we crossed the Bering Strait and came to Brazil. So things look similar, but they're not. So what you would imagine, a power of you would argue a cat's a cat. So Google can take 1 million pictures of cat and still would have cats. And the nature is a little bit more complicated because ecosystems are highly variable. And local knowledge is essential. And we have a problem. And the problem lies in our language, in the way we relate to objects in the world. So the problem is that we describe the world and we give the world names. We give the things in the world a name, a mountain. But how big is a mountain to be called a mountain? So there's a huge debate about we use a small number of categories to describe the world. Do they describe all objects? And this question is more, it's not only a, let's say this question, if I frame it this way, goes back to Aristotle in his categories book, but it becomes interesting when I try to actually say, well, what are the principles of machine learning? The principles of machine learning, of course, one of them is there is nothing but the data. The data is the data is the data, and the data gives me everything I need to know about things. Yes, but we label the data. But what we label as forest is different in different places. So you have 4 pictures here. Each one of these pictures depicts a forest. And of course, they couldn't look more different. And from the point of view of the satellite, their data, which is the data which is measured, is completely different. So you have a tropical forest, like for example, in Brazil, or you have in Congo Basin. You have temperate forests like Siberia. You have dry forests in Brazil, for example. There is a dry land, so where dry forests. And of course, there's planted forests. So we use the same word, but if we try to the machine learning methods to learn about this and use the single word for it, we might be in for a surprise of the inability of the method to distinguish what is a forest. Things get more complicated than that. Human beings are very good at simplifying. So we take just one example, a cerrado. Cerrado is the Brazilian savanna. Now, it's a region that ranges from 5 degrees south to 25 degrees south. In other words, it's almost close to the equation, from the equator to Capricorn, the whole tropical region. And we talk about savannas, and of course, given there's so much a latitude gradient here, you would imagine there is, of course, different things we call by the same name. Indeed, the term cerrado in Brazil applies to completely different things. It applies to woodlands. It applies to areas where there's mixed small trees, some trees, grasslands. It applies to this prairies with open cerrado. In fact, there is a huge amount of variation. And of course, and then it becomes a problem. Machine learning likes labels. And if you say, oh, I have a single label and a lot of different data to train with, you get in trouble. And if you say, okay, the problem is solved by in breaking the label down in so many small labels. So here from you can see on this picture that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different labels which actually apply to the same big name. And of course, my problem now of finding good samples is multiplied by 14. Instead of finding 10,000 samples, I need to find 14,000 samples. So I now have a problem, is if the more detail I want to describe nature, the more it becomes hard for me to ensure that the labels I'm giving to any machine learning algorithms are consistent and they are the same. But it doesn't stop there. A simple question: when is a forest not a forest? In other words, when does a forest cease to be one? Of course, you hear every day, and this has been my bread and butter for the last 30 years, is deforestation. But what exactly is deforestation from a machine learning point of view and for an algorithm point of view? It's an event. It's an event in a certain sense. It's a series of events by which a pristine forest is first degraded by logging, then someone puts a fire, and someone has a clear cut. So it's not one specific place, but a series of happenings that start from a forest, beautiful, lots of trees, very close canopy, to a completely devastated land. But it's not born overnight. In fact, it may take years for the whole clear-cut events to take place. What do I do with the data? How do I feed my algorithms? in the case where things are changing. And that's precisely one of the issues that we are not good as humans. Neither are many of our algorithms to deal with time, to deal with changes in time. One thing is to have a time series of the value of Apple it's a time series of the values of Apple, and we know that there are extremely external events that change that. And these are the hard ones to predict, the so-called black swans. And this is a paper, a recent paper by Robin Chadson, who says, look, there might be case one where there is a natural forest which hasn't been undisturbed. Or maybe let's look at case two, where someone there and destroys. It's like someone has destroyed Apple and the value is 0. Or there might be a breakdown because of, some kind of accident, things that happen. And then, of course, the breakdown is such that it can come back again. So the bottom line here is we need to measure not only what exists in a certain place at a certain moment, but what actually has been the evolution or the events that has happened there. And based on that, the problem of Earth observation and machine learning becomes more complicated, because the problem cannot be reduced as image processing and recognition of images like you do face recognition. It actually involves working with space and time. And working with space and time means that you would have to have some kind of spatial temporal models, which again are tough. And what do you do when things are changing? It's training machine learning models is extremely tough on this. I personally have been leading a group in the last 5-6 years to develop satellite image time series analysis using machine learning. So I'm sharing a little bit of what I found with you. This is called SITS. So SITS is an acronym for Satellite Image Time Series, and it's on GitHub. So everything is open source. And what we do, we basically do a lot of work in terms of obtaining the data, organizing the data. So in the left side, you see, well, we organize the data. But then the parts marked in yellow are the ones which are really hard. How much data do you need? Oh, enough to describe all of the categories that exist in the land. How many categories there are? What is the level of detail that I want? And what is my capacity to collect data that actually describes this level of detail? And this is the crucial bit that controls the behavior of the classifier. So this is an example of many of our works and many of the papers in the literature use the so-called 5-fold validation accuracy or K-fold validation. And this is, for example, this is 33,000 samples of the Amazon, and the 5-fold validation, I mean, you may recognize some of the methods, SVM, random forest, the deep learning perceptron, ResNet, and everything. And everybody gives 99% accuracy. And of course, this is when you look at that, you realize you're in deep trouble. Anytime you get this kind of accuracy, you say, I'm in trouble. These models fit the samples, but they don't represent reality. So in other words, you have samples that match, models that match the samples, but they don't match the reality. I can assure you the actual behavior of the model is much worse than that. So to sum up with the challenges, I'm trying to keep the whole discussion brief. You need to think of time as an element that you need. For example, how do you recognize events on a time series? So These are recent papers that we've published there about, which is something which is not considered to be machine learning. I don't know if it's machine learning or not, I don't care. This is a dynamic time warping, weighted by time. So it's a time series classification measure, which gives very interesting results in recognizing events. I'm not going to detail, the details would be later on. But essentially, the whole deal here is that things change in time. And in case of nature, for example, there are cycles, the cycle of the seasons that applies to a thing like the pasture, the cycle of sowing and planting and crops that apply to crops, for example. So these natural cycles need to be, it's not, sometimes you have a success using them in machine learning, but I can tell you it is not a piece of cake doing that. So to sum up, what we have, the problem we face is that the diversity of nature and the fact that our language is ambitious limits the work of machine learning in big data apps. That does not mean that we cannot use it. Yes, we can use it, but we cannot say we're going to break the bank with it and we're going to save the planet by itself. Yes, big data enables continuous monitoring of the planet, but you cannot think of the problem as a recognition of cats and dogs, a recognition of faces. You need to model time and the events that happen. And that's where machine learning has a hard time when you try to teach it that things must change. And that's where I think, I don't have an answer, I have a question, that the inclusion of some kind of semantics would improve machine learning for big Earth observation data analysis. So thank you very much. I hope I kept within the time allocated at 20 minutes. And I hope that I was clear enough so that people from different backgrounds could understand the points I was trying to make.
So I think, Gilberto, it has been a wonderful talk. Thank you for being, a part of MKAI, and it's so much, it's a favor as such when we know your background and so much that you have done on deforestation. And I totally understand where you're coming from, that we have such amount of comprehensive source of data from the satellite images. But how difficult it gets when you actually apply the machine learning to it, especially the labeling part to it, to the classifiers, arranging for the large amount of training data that needs to be associated with it, understanding or having a local knowledge of the environment. And I think, yes, I do agree that nature undergoes physical changes. It is more complex, and having the temporal dimension to it will only make the ML models more robust. I think, therefore, we have to associate to the functional ecosystem models that we have. I think that is where we will be able to use the observation data very efficiently, but that can help us to solve the global environmental challenges. It's not just deforestation, we know, but even any climatic hazards, or the crops, agriculture, etc. So I think, Gilberto, I have summarized your talk, and over to you, Richard, if you want to take it from there. Thank you.
Thank you so much for the summary, Jason and Gilberto. Thank you so much for that. I see there's a number of questions that are already coming through. If I take them in order, and Jason, you're more than welcome to pick this back up again. Jitendra had a question. I'll give you a chance to ask it yourself before I step on your toes. Are you there?
Hi, Richard.
Oh, hey, how you doing?
Thank you very much. It was quite fantastic, actually. Thank you, Gilberto, for that one. Yeah, it's quite good to know about all these things, actually. And I work on a little bit of mini project type of thing in the, like, when I was doing some project on the forest type of thing, like identifying where it's a forest. Actually, it's very difficult to actually do the labeling and everything. But just a quick question on this one, because I found that for a normal public, when they wants to do some big project or wants to get some access to the data, that's the main problem. Because yeah, there are some data available in the Kaggle, but that's not quite useful to them, just apart from practicing or just knowledge building type of thing. Is there any chance that actually normal people also have access to the data, they can, and also if they wants to know actually where they wants to contribute something to your project or something like that, is it possible?
Well, yes, of course, it's possible. I said I put a GitHub link for the software. As for the data, I mean, Gregor, next speaker, will tell you all about where to get data because he's the man behind the Sentinel Hub. So I would defer the answer to Gregor because he would have a wonderful answer. I mean, the data is basically open. I mean, most of the data is basically open to the Sentinel Hub. The training data I've used in my projects is also available. The base data, what I mean is the data from the satellites is available on the places like the Sentinel Hub, and the training data is available. I'll put the link there to share. So essentially, this is basically the work that I do. So the baseline is to make progress, we need to share. We need to do open science, and either on the building. I found it building software collaboratively in GitHub seems to me one of the possible ways by which we can make progress together.
Okay, thank you very much, Gilbert. Thank you.
Thanks, Gilberto. I think we have a couple of questions we can take in here. We have some more time on hand. So Delphine has a question to ask. Delphine, would you like to go ahead with it, or you want me to read it out to Gilberto?
You can read it out, please.
Yep. Okay. So on the forest part, does it mean one has to train or define their model in order to not to be biased in analyzing the data? That's
yes.
The question, Gilbert. Yeah.
No, the problem here is not to. You have to. The training of the model is the one that controls. I mean, it really doesn't matter if you use a basic random forest, or if you use a temporal convolutional neural network, or a deep learning with 25 deep layers. What controls the quality of your work is your training data. All the rest is completely superfluous. I mean, superfluous, you may get a 1%, 2% improvement, but that's statistical noise. So the training, the real training is very careful. It is the one that controls the quality of the output. I don't know if that was the spirit of the question.
Delphine, does this answer your question? I hope it does. We can move on to the next one. So Neeraj has a question. I'll put it here. So with so many new satellites under development, what do you think are the key issues in extracting information from their observations and making use of it in terms of an ever-growing variety of applications and services?
Well, the key issue here is I mean, the satellite is there, but you need to organize. So first point is organizing the data into what we call data cubes, which are reproducible, which are basically consistent observations over time. There's one technical bit here. And the other thing is we need to share. What has happened in this world is that we have jumped one step which normally in science is the step done at the universities. there is a huge amount of companies who have started to produce services based on Earth observation data, which is not backed by science. So it's not so difficult to start up a company to generate products out of the open data. Now, how good are these? So, I mean, could AstraZeneca have developed their vaccine if Oxford had not been researching these DNA vaccines, for 20 years? So we're making it, I mean, we're making this as it's already in terms of Earth observation, things are already application ready, and things are already, I mean, it's just a question of entrepreneurship. It's not just a question of the entrepreneurship. There are scientific issues which are not answered, and no amount of entrepreneurship has ever replaced science, in my view.
Thanks so much, Gilberto. And we have a few more questions that I will be asking here. So one of the question is from Andrew. What drives the algorithms with high accuracy, but not representative of real world performance? Is this due to a pressure for publication?
Well, it is due in the case of publication. Yes, it's due to pressure of publication, and it is due to flawed, and I speak flawed again, flawed methods of evaluation. Essentially, what is happening is people are publishing papers using validation in terms of accuracy. So if you go through the literature, you see that the guy has, if I have a 5-fold or 10-fold validation of my samples, and I say this is the accuracy of my product, these are two very different things. And this is what the people are accepting in the literature. There is, I have an accuracy of 97%. Accuracy of 97% in relation to the samples. Even if you say 50% of my samples, or K-fold means that I take 20%, 5-fold, for example. I take 20% of my samples and save them and train with 80%, and then I change it 5 times, or I can do it 10 times. You're still dealing with your samples. You're not dealing with the real life. So this is completely self-delusion. But unfortunately, in the literature of Earth observation, this is accepted. And in much of the literature of machine learning, this is an accepted way of saying you have reached an accuracy. And this is completely misleading, because there's a huge amount of bias in the terms of selection bias when you select your samples. You tend to select samples which are good, which inequivocally represent a thing in the Earth, and the Earth is not necessarily is the same everywhere. So most of the techniques we use are flawed by construction.
Thanks, Gilberto. I hope it answers Andrew's question. We have Anna who has a question. Anna, would you like to ask the question yourself, as you have said you would like to ask it yourself? Can you just unmute and talk? Yeah. I think Anna is still on mute. Okay, I'll go on to the next one. So Sadaf has a question. So I have a question with respect to Sentinel-2 land images. Recently, I have trained a transfer learning ResNet-based NN classifier using Eurosat dataset. My accuracy on Eurosat is satisfactory, but Sentinel-2 images processed in a different way give very low accuracy. Do you think there are some issues based on which it is working better on Eurosat only and not the other dataset? I know this is a technical question, yeah.
Well, I mean, there's a recent paper, I'm trying to find out, there's a recent paper on Google that Google guys presented. It's somewhere, maybe Richard knows. I mean, essentially the problem is the same data set with some twitching of the algorithms gives you It's uncontrollable, the prediction. The problem here is I'm not sure, and again, I am not sure what your measure of accuracy would be. The argument would be accuracy should be complete. Doing accuracy in using satellites is extremely difficult because it requires you to have a set of accuracy measurements which are completely unbiased and not are pixels or objects which are not easy to classify. And that's why I'm not sure, and that's why it's not unexpected that different training data sets give different training resolutions, especially if your accuracy is measured as regards, like with using k-fold validation. So you're not measuring the quality of your classification, you're measuring the quality of your data set. And that's not necessarily that your data set is representative of what you want to clarify. This is a problem I face every day, and I don't have an answer. I just tell you it's relatively impossible to solve.
Yeah, I think there's an additional question from Sadaf from that regard. She would like to add that I'm not sure that the two images are different. Either it is L1C or L2A processing. I cannot say for sure, but I just want to know what other reasons could be possible for this bad performance.
No, I think you're just welcome to the club. Welcome to the club. I can, if you want to cry on my shoulder, I can cry on your shoulder as well. Don't think you're the first one that faces it. This is my daily life, and I'm sure daily life of anyone. My student comes, it works, and the next day he says it doesn't. So I mean, this unpredictability and this craziness that one day it works, the other day it doesn't work, is a reflection of how badly we control, how sensitive the parameters in the whole issue is how unstable the whole function is. It's essentially what is. It's a problem of function instability in the classification. Welcome to the club. That's just, don't think you're the first, and unfortunately you're not going to be the last.
So we'll just take one more question, Gilberto. How do you decide the amount of time series data for a particular task? There are many causes for deforestation. I imagine we cannot use the same time period data for all the varieties. We will need some amount of time series data for fire and different amount of data for clear cut. So how do you decide the amount of time series data you need? Is it manual process or automated?
Thank you very much. I mean, this is the question I've been asking myself. Certainly not an automated process, because you need, essentially, currently, we don't have a good method for deciding this. You are absolutely spot on to say that if I take a time series of 12 months, it works for things that happen during 12 months. But if the clear cut has happened in 3 months, this will not be considered. But if I take a time series for 3 months, things that take 12 months to happen will not be considered. So what essentially I was telling, and that you have congratulations, you have hit the hammer on the nail. That's when times get things, and things happen in your world, in your universe, in the Amazon, for example, at different times, and take different periods to change. Some things changes in a year and a half, some changes in 6 months, some changes in 3 months, some changes in 18 months. So now you are in trouble, because putting a single machine learning capability to deal with all these cycles is extremely tough. That's what I'm saying. This is essentially what some of my research is going now. And the problem is very well put by you, and I'm trying to find an answer which I don't have at the moment.
Thanks so much, Gilberto, for your talk and answering so many questions. We have some more, but we will do that later in the Q&A session. Richard, can you please come over and move on with the next speaker? Thank you.
Thank you again, Jason, and thank you, Gilberto, and thank you for all of those questions. Gilberto, there is still one in the chat actually just asking if you can put a link to that paper, if you wouldn't mind grabbing that one directly in the chat. And please just share your gratitude with me, if you will, in the chat or with your icons and emojicons, just to show our real appreciation of Gilberto to come spend some time with us. As you can imagine, he's got plenty of things leading into his schedule, and we're very, very grateful. Thank you, Jerry Chandra, Niraj, just see others thanking him. So it gives me great pleasure